Thank you, Alexandris, for introduction and for inviting me. It's a pleasure to give a talk at this place. So the work I will be talking about is kind of like based on several papers that were carried out under support of the Simons Foundation collaboration in wave turbulence, so which I acknowledge here, and also we did a lot of high performance computing that was provided by the wonderful facilities of this French establishment, GENC, very powerful super computing clusters. So to first introduce our group NIS, so apart from myself, so this who is at INPHYNI, as Alexandra said. So there is also Georgi Krusovich at the Lagrange laboratory at Observatoire de la Côte d'Azur, the Côte d'Azur University, and the postdocs, Yin Zhu, Boris Semisalov, and also presently Vincent Labert. So, so I also want to just kind of dedicate my today's presentation to the great man, founding father of the subject and wave turbulence and many other research fields in physics and mathematics, who unfortunately passed away just half a year ago, Vladimir Zakharov. So just a brief outline of the talk. So introducing wave turbulence, so there will be kind of like several parts I would like to talk about. So first of all, wave turbulence is a certain statistical description that one can put at test by via numerical simulations, and that's what we are going to do. And also there are several theoretical predictions that we are going to test for stationary as well as evolving scaling solutions, as indicated in the title. And also I'll discuss some implications of some of such solutions in terms of non-equilibrium Bose-Einstein condensation and the blow-up of the underlying dynamics. So, but first of all, it's a very general introduction for wave turbulence. So just give you a few examples of what is wave turbulence. So wave turbulence is essentially refers to in physical system that can be under very different situation. There can exist waves that are can interact one with another. And such if such waves are sufficiently random and they cover a broadband range of scales and a broad range of wave numbers and directions, so they start interacting with each other. You can describe the spectrum, and that's the subject of wave turbulence. So in one most well-known example, in surface sea waves, which are the study of which is important for predicting the so-called the wave weather, important for navigation, for outshore industrial activities like oil drilling and so on, and so on. And also they are important for say, exchanges with atmospheres as a part of the climate dynamics. So as far as, so that was water surface wave. So one experiment here on the capillary waves at zero gravity. So that an experiment that was done by a group in this particular laboratory, Stefan Fof, Eric Falcon, so and was Umberto Bertoloso at that time, I think, flew airplane, and then they went to parabolic flight at zero gravity while they was 20 seconds in that free fall. They were doing this experiment. So why? To reduce the minimize effect of gravity so that you see better effect of the surface tension. So this kind of photograph from their experiment. Waves in rotating fluids, and as well as waves in stratified fluids. They're both examples that are very important for geophysical fluid dynamics. As you know, our atmosphere is rotating, and also it is, the air is stratified, and you have respectively internal and inertial waves propagate, and that affect a lot of processes in particular in weather and climate dynamics, and in particular for, if you were talking about stratified fluids, it's one important and still unresolved issue. It is believed that these waves in internal waves are responsible for mixing in the ocean, responsible for kind of closing the conveyor belt circulation, right? The global general circulation to bring hot masses of water from the bottom of the ocean back up, right, to the surface. So it's believed it's done in gradual wave by internal waves, but what is exactly how to describe exactly this mathematically is still biggest unknown, which is in climate models is done in a very empirical way, which would definitely require further study and improvement. And so on. That's where wave turbulence is important, because it's precisely this nonlinear wave interactions that would lead this transport. So another example to mention, this is a lot of waves in plasmas, in particular in fusion plasmas. And so like tokamak shown here, the device being under late stages construction in Cadarache. The reason why this device is so big, you see this man here hanging, so that gives you a scale of the device. The original idea of this device was by Artsemovich, so it was just was the first tokamak T1 was a little one on tabletop, and the reason why it went to such a big scale is precisely this loss of energy and particles from plasma core to outside, right? And so. And this is because of anomalous transport, as you can see here. Plasma turbulence is developing, but the plasma turbulence in big role that is played by waves. In this particular example, drift waves, and it's a reason for loss, but it's also a reason for hope why this can be this problem can be overcome, because this particular wave turbulence of drift waves lead to anisotropic inverse cascade of energy, forming zonal flows, the flows that will be along the small radius, that will block the transport of heat and particles from the core to outside. So it will insulate. It's got the process called LH transition, which discovered experimentally in smaller devices like D3 in a long time ago, and it's built into this engineering of this particular new tokamak here. So again, the reason why it's so big is just to sort of make it harder for heat to get lost from the center to outside. So it would have a bigger path to pass through. So MHD waves in solar wind. So solar wind, shown in this diagram, is made out of conducting fluid, plasma, and and the solar wind is very turbulent, and the biggest and the a big role in that is played by Alfvén waves and interaction Alfvén waves. In fact, so this weak wave turbulence of MHD waves is one of the main reference theories in the theory of MHD turbulence. And so we had a paper on that, and it turns out to be one of perhaps my biggest cited paper. So that kind of some 700 citations. So that indicates that it's really one of the reference theories to which other developments always need to be compared. So anyway, but today I was not going to be talking about all these examples that I just briefly showed, but I will talk about something that has to do to applications like Bose-Einstein condensates or nonlinear light, or even the early universe, cosmological evolution. So what these three different examples have in common is the master, the nonlinear model, a master nonlinear model that is often used for modeling these applications. And I'm going to be talking about turbulence in this system. So this is called Nonlinear-Schrodinger equation, sometimes also called Gross-Petevsky equation in context of Bose-Einstein condensate. So equation for some complex scalar function, and it is a function. It is a scalar field in 2 or 3 dimensions. So in my talk, I will be dealing with 3-dimensional systems. So this system, what is wave turbulence for this system? So the first of all, so if you look at this equation, right, and you say you have a weakly nonlinear system, so you can neglect the last term, which is nonlinear, right? And you have a usual Schrodinger equation from quantum mechanics textbook, right? And then it will have a wave solution, right? So if you substitute that into this equation, Laplacian immediately gives you k squared factor, time derivative gives you omega, and so you will see so that a solution exists with a frequency given as a wave number k squared, right? So now wave turbulence considers weakly nonlinear systems, and so therefore we need to go to next order. So in linear system, waves I can have simultaneously waves present with different wave numbers. And because of system is linear, it will be linear superposition principle, so they will not exchange energy, the amplitude will remain the same. So if I take into account nonlinearity, they will start exchanging energy, such waves. But if nonlinearity is small, this exchange will be slow. And the idea is to use this fact, this separation of scales, wave period and the exchange of energy between the different harmonics, to derive the kind of average description, and that's called wave turbulence. And it's usually derived for this object, which is called the wave action spectrum, which is formulated here, where psi k is the Fourier transform of the field psi, and system is considered for simplicity in a periodic box with of size L, and D is a number of dimensions, which I say later on will be mostly 3 in our case. So the conditions for such theory will be, first of all, that the time of nonlinear exchange between the modes is much bigger than wave period, which is 2 pi over omega, right? But there will be other condition also, that the so the waves has to be weak, but not too weak, because let's illustrate it on let's consider in physical space wave packets in a box, right? Think of a statistical description of just gas, and you want to derive Boltzmann equation. The condition to derive Boltzmann equation, that mean-free path of this for such atoms or molecules, has to be much smaller than the size of the containing volume, right? So this will be opaque gas. You can derive Boltzmann equation. Otherwise, it will be Knudsen equation that will be Knudsen gas that will be very strongly affected by the shape of the containing volume, right? Same thing here. So we need that our waves, our wave packets, actually mean-free path of them is much smaller than size of the retaining box, right? And mean-free path is determined by the nonlinear interaction. So you can interpret sort of the nonlinear interaction as a sort of collision. And if you do that, so your mean-free path is much less than size of containing box. So and then in terms and then the mean-free path you can say express in terms of time between the collisions, which will be nonlinear time, interaction time, and velocity multiplied by velocity, which is group velocity of and so you get this then condition for the second condition for for applicability of such kinetic description. So you see, in other words, we have double inequality. So the nonlinear time has to be waves have to be relatively small nonlinearity, but not too small so that the finite size effects are not important. And so this is important for the theory. Right. Okay. So there are some, this is a big, deriving kinetic equation itself would take some sort of a mini course, and it's been done many times in various places and books, including my own. So I'm not going to, I just told you about the conditions and which I assumed, so I'm not going to reproduce these derivations. I will spend time more on testing the result. So the result is under these assumptions that I mentioned, is the evolution equation for the spectrum of wave action. And the only thing you can notice that this equation is kind of analogous to Boltzmann equation for particles. So k you can consider as distribution function. K is a momentum space. You can see here two delta functions in k and omega. This is kind of like conservation laws for momentum and energy in Boltzmann dynamics, right? So there are a lot of similarities. And in fact, even it's not accidental at all, because there is a more general kinetic equation called quantum Boltzmann equation that has two limits. One of them is a classical Boltzmann equation, Maxwell-Boltzmann, and the second one will be this equation, wave-kinetic equation. So one of them is classical particle, one limit, and the second one is classical wave, right? So one is applicable when you have rarefied gas of atoms, another when you have dense, so that you have within the de Broglie length, you have many particles. That then they will be coherent, they will form kind of a classical wave. Right, and so I mostly want to talk about the now the testing this theory, because you see these assumptions that I mentioned, double inequalities, are very hard to satisfy, you know, numerically and experimentally, and it's always it's never clear how well the theory will work in reality for describing the real fluid motions. And so to test, so we put we do a direct numerical simulation of three-dimensional defocusing NLS, our master wave nonlinear model, and the associated result in the wave-kinetic equation. And so we start with some initial condition restricted to some region in Fourier space, and then we run a simulation, and you see so we have two in two simulations, and so NLS, or actually so Gross-Pitesky equation and wave-kinetic equation, and you see at early times it seems that they are really quite well agree with one another. So, and of course that we can also check wave turbulence hypothesis by doing spatial temporal Fourier transform. So in addition to in Fourier space, we also do time Fourier transform over the particular window of time. And the condition that the gas of wave packet is opaque should be in these terms, in terms of omega, is that the thickness of this distribution around the linear dispersion relation omega equal to k squared has to be bigger than the distance between adjacent eigenmodes. Right, so you kind of then you have this continuous limit, okay, and if you do that, you measure this thickness and you put it on a graph for different wave numbers. So these are the blue dots, and you see these two conditions that I mentioned on the previous slide of applicability, so double inequality. So I do have a significant number range in which I am really satisfying these two conditions, but I have also a range where I'm not satisfying, I'm falling out of it. And also remember that, like in any mathematical theory, it's a double inequality. It's a strong inequality. So I'm not only supposed to satisfy them, but satisfy them strongly. And definitely, I'm not satisfying them strongly, right? And yet, you see, so the theory turns out to be very robust, that even that mild agreement with conditions leads to very good performance of the resulting statistical description. So that is agreement for about two kinetic times. What's kinetic time? Yeah, please. Say again? So this is exactly a measurement of just from numerics. We measure the thickness of omega distribution right? So in other words, the broadening of a resonance has to be bigger than distance between nearby eigenmodes of the periodic box, right? So that, and so which is easy to understand if you think that here's the amplitude, right? So this amplitude, when it's changing, then your wave is not exactly at just that frequency. It's also somewhere to some distribution around that. Okay. Yes, and so the agreement is quantitative, very good until about 2 kinetic times. So what is kinetic time? It's characteristic time of associated with the kinetic equation. How do we measure it? It's very simple. So we take we take time that is required for initial peak maximum to get twice smaller. You see, this is a log scale here in this. Now I don't have cursor. Okay, so you see it's a log scale, and so when that peak reduces twice, it's kind of like we take it as a measure of characteristic time of evolution, and we see that this kind of thing is virtually impossible to prove mathematically that this should be true. It's kind of like a numerical experiment proof. Same for Boltzmann kinetic equation. For Boltzmann kinetic equation, there exists no proof that it's valid for characteristic kinetic time, only for small fractionated. Okay, it's Lumford theorem result. Okay, so in this case, so we see that, but of course everybody is using Boltzmann equation, and it's tested many times that it does work for at these characteristic times. So now. So now with other things, we actually we can also look not only at the spectrum of turbulence, but also at probability distribution. Mm-hmm. Yes, so I'll show you just in a minute. How it works for longer times. So, and here I just want to mention that spectrum is only one statistical quantity. It's average or square amplitude. But you can have, you can deal in this theory with the whole distribution of probability distribution of such wave amplitudes. And it's usually assumed that that it's Gaussian, but it's not necessarily true. For example, in numerical experiments, one can start with deterministic amplitudes and random phases, right? As shown in this picture here. And with evolution, it will tend to Gaussian distribution, which is an exponential graph, means a straight line. And you do see. Well, there is a theoretical prediction in solid line and numerical results do agree very well, not only for spectrum, but also for the distributions. Yes, so essentially what's assumed in wave turbulence for derivation, right? So you take Fourier coefficients, right, which are complex functions, right? You say, okay, so in this Fourier, well, first of all, you assume that they are initially statistically independent from each other, okay, and also that the phases of them are random, uniform and from 0 to 2 pi. But you don't need to assume anything about statistics of amplitudes. So it could be either just purely deterministic, or they could be Gaussian, or exponential corresponding to Gaussian complex coefficients, right? And you can have evolution for that particular distribution function of amplitude. So phases are random, but amplitudes you can follow evolution. So randomness of phases is enough for the clue. And then you can look at steady, and you can look at unsteady and how it tends to steady. So this is different moments of time, and steady would be this, exponential distribution. So a long time. Okay, so you see now we are moving to times up to about 10 characteristic kinetic times, and you see that indeed we start observing differences. Qualitatively, it's quite similar, but you see that so that the NLS front here lags behind, so propagates slower than the kinetic equation. And there are deep reasons for that, because, well, first of all, NLS is on a discrete grid, because it's periodic system, so k-space is discrete, whereas in a kinetic equation you take continuous limit, and as you go closer and closer to smaller k, your discreteness is going to be filled more and more. And nonlinearity grows, turns out, in a real system, an NLS system. And so your condition of weakly nonlinear waves start breaking down. And to add to all of that, it turns out that the kinetic equation blows up. And you experience I will talk about that in a minute. So it experiences the blow-up solution at 0k, infinite time. It shoots to infinity. And that is kind of non-equilibrium Bose condensation. Whereas in Gross-Petaevsky or Nonlinear-Schrodinger, you don't have this phenomenon. Okay, so that condensation will never be just in k equal to 0 mode. It will be some distribution in some small but finite wave numbers. Right. So but first of all, let me just move to another subject. Other type of waves, the steady states. So the simple, so examine what are the theoretical predictions, and first of all, first is a very simple one, is when this this round bracket there, on the top, is equal to 0, right? So it makes the integrand 0. So that is realized on this Rayleigh-Jeans thermal distributions, right? So these are the classical wave version of Bose-Einstein distribution. So it is a limit to Bose-Einstein distribution in terms of classical waves. Easy to see that it is satisfied because you take 1 over n, you will have omega k plus mu, right? And because of the delta function of omega, mu will cancel, of course, and because of omega, it will be 0, right? So this is kind of absolute equilibrium. It actually realizes maximum of entropy. But that's not the, and so, and of course, when system, you start, there are two conserved quantities in the system, total number of particles and total number of waves. And so if you start with, so the in initial conditions start with certain number of particles, certain energy, that will determine what kind of constants T and mu you will have in the final distribution, temperature and chemical potential. So that, except that sometimes for some combinations of N and E, you won't be able to find such T and mu. You won't be able to fit with Rayleigh-Jeans distribution. And that indicates a particular situation where there will be blowup, where instead of a Rayleigh-Jeans distribution, there will be there will be at k equal to 0 mode, at 0 frequency mode, there will be accumulation of particles, macroscopic number of particles. So that is thermodynamic equilibria, and they are not the only ones steady states, and in fact more interesting ones are turbulence-like solutions, cascades. So just to sort of remind you the picture of classical Richardson cascade and turbulence, right? So that you excite with forcing large eddies in a classical fluid, and then due to their mutual interactions, they break into smaller ones, and then smaller ones and smaller ones. And if viscosity is small, so they will pass their energy to smaller and smaller eddies. So the flux through scales will be constant until you reach viscous dissipation, where it's going to be cascade will be stopped. And so the state will be determined by the flux of such process. And in wave turbulence, you have a similar picture, except that the cascade will happen not from vortices bigger to smaller, but from longer waves to shorter waves. Or if it is inverse cascade, it could have also in the opposite direction. So in Fourier space, this process can be seen as you go from low wave numbers to high wave numbers, from lower momenta to high momenta. So if you have two conserved quantities, as in two-dimensional turbulence, so the energy and entropy, which is Vartisti squared, in two-dimensional hydrodynamics, Euler equation, then it was predicted by Fjord of 93 by simple contradiction argument that these two quantities must cascade in the opposite directions in Fourier space. And so therefore, moreover, energy will cascade to lower wave numbers in difference with 3D case where it was other way around. So that's why it's called inverse cascade. No, that's just example. We'll come back. Come back. It's just an example. Okay, so in Schrodinger. Okay, I'll discuss that. Okay, just give me a little bit of time. Yes. Yes. So the okay. So that's dual cascade. And yes, come back to now Schrodinger. We have two conserved quantities, and we same kind of Fjord of contradiction argument leads to picture that energy must cascade to higher wave numbers and particles in lower. And that's now. Let's come back to your question. So what does it mean physically? Where's dissipation, etc.? So you can interpret that particular case in case of Schrodinger equation very nicely as if you imagine your system in a trap, and you shake your trap, as indeed was done quite well in experiments of group of Nir-Navon. You shake the trap, and you create some intermediate excitations with intermediate wave numbers. So then, according to the dual cascade picture that I showed before in k-space, energy must cascade to higher and higher levels, and particles to lower and lower levels toward the ground state. So you can think of it as a non-equilibrium condensation. And energy, right? So this is a picture from our paper 2003. You see, we put this finite size of the trap, right? And so this is where the dissipation is. So you lose it outside of the trap. And in fact, it was realized in the experiment. They called it synthetic dissipation. They actually did implement the finite height of the trap so that to observe precisely this cascade picture, so that you don't have sort of thermalization or whatever, you let the flux out. So you can think of it as evaporation of molecules from cup of tea, right? So evaporation or cooling. But of course, it's not nothing to do with evaporation or cooling as a technique of creating condensate itself, but in some sense it cools the system here, right? Right, okay, so then what are the predictions? Okay, so the predictions for such steady states, which are equivalent to famous Kolmogorov spectrum, analogous. Called Kolmogorov-Zakharov spectra, right? So basically they are scaling solutions. If I assume solution of this type, then in fact I can, okay, so show analytically that there may exist solutions of the kinetic equation, steady solutions. And that is done, so I'm not going to go into detail, obviously, because of short time, but just to flick through that, it's a so-called Zakharov transformation, very ingenious transformation that actually showed that, you know, so transforms the you see, upper line kinetic kernel to that one, so you acquire another bracket. So you map one region of integration onto another, 4 regions, 3 mapped onto one. And you get that. And then when you have condition, a new solution where another bracket. So first bracket equal to 0, it's Rayleigh Jeans. Second is Kolmogorov-Zakharov. But so it turns out that because this procedure is not an identity transformation, you can get spurious solutions. That's why you should always check after you've done that your integral is convergent and you have you know, so good mathematical solutions, right? So it's essentially, so what we get is this way. We get 2 values for the exponents of this power law spectra, one corresponding for direct cascade of energy, another for inverse cascade of particles, right? And by checking locality, so that we need to check that the original, before the transformation, the integral is convergent and is 0. So we have the condition, first of all, for the convergence if you have arbitrary power, so that these two indices has to be in the range from from 1 to 3/2. It's a region of convergence. And you see that one of them is precisely on the borderline. So potentially a problem, right? So it's actually means it's logarithmically divergent. In fact, what happens is you can calculate this. So this is what we plot the value of the integral before and after the transformation, right? And you see they coincide where integral is convergent. And one of them, you see when it's 0, it's the inverse cascade solution. It's a totally good solution. But for forward cascade, we see interesting thing. After transformation, of course, it is 0 by construction, Zakharov transformation. But if we check the integral before transformation, we have a finite value. It's convergent integral, but it's not 0. That is quite a strange situation. In fact, it's an analytical calculation. So this integral is computed analytically. So if it is not 0, this means the right-hand side of kinetic equation is not 0, so it's not a stationary solution. It's bad. And we need to do something about it. Okay, I'll skip the details of how other checks as stability, for example. But okay, so we need to do something about that. But let's first of all consider the good solution, right? So you see, in addition to this exponent that we found, right? So xq, we also have a refactor, which is also important. In classical turbulence, it contains the Kolmogorov constant. This is a good check to measure this constant, you know, and here we can have a prediction. So if we, in fact, calculate, for that we need to calculate this value of right-hand side integral and express it in terms of the flux of particles, which is defined as as shown there before, Q capital. And so we have a prediction of, in fact, it's an analytical prediction again, some crazy number in terms of hypergeometric functions, but with any arbitrary accuracy, we recover a number which then we can test whether it's realized in numerical simulations. Okay, and so, and indeed, so we do numerics for both NLS and wave-kinetic equation in this setting. So we're only interested here in inverse cascade. So we force at high wave numbers and dissipate at low wave numbers to produce a steady spectrum. And the results are shown here. The results, as often in turbulence, we compensate onto the expected solution. So we divide the result by what we expect, and so if it is 1 everywhere, so it's that very case size. And you see, so we see a good agreement. So this means we're not only checking the exponent, we're checking the constant as well. We see the NLS at 2 different resolutions, 512 and 1024 cube, and the kinetic equation. So they all give pretty good in this range, good coincidence. So now what's the vertical line here is where it's so-called the scale, the Hillen length scale. So that's where actually weak nonlinearity assumption breaks down. So all the scales here to the left of it, they are not satisfying the assumptions of wave turbulence theory. So we should not be looking that way. Okay, so and for now come back to direct energy cascade. So now to fix that problem, that actually a pure power law spectrum is not stationary, we introduce a logarithmic correction, right? So in fact, it's a logarithmic correction, you know, when you have marginally divergence at physics often, you know, invoke logarithmic corrections. And in turbulence, these kind of corrections were done a la Kraichnan, who did it for 2-dimensional turbulence, but on a hand waving level. So here, in fact, we can do exactly asymptotically, we can derive this correction, Why is it important? Not only to prove that it is correct, but also to obtain prefactor, again, the prefactor constant. And so by doing that, so we get the, by seeking solution in this form, so we get this result, and we get not only that log correction, but also a prefactor constant. And then we set up numerical simulations now with forcing at low k and dissipation at high k. And now, before I mention our result, I come back to the results of Navon experiment in that shaking trap. And you see, so that's the results, and you see the best fit was the power law with exponent minus 3.5, whereas the Kolmogorov-Zakharov prediction 3. And so that remained a mystery. Why is it so? So what follows from our study that it's actually not a modified power law, but in fact it's log corrected power law. So here we put together compensated spectrum, and we put also, so we put the one without log correction, k cube, and we put the one 3.5 as in Navon, suggestion of Navon. And we see that clearly log corrected fits much better, including the prefactor constant as well. So in fact, that particular paper, so that illustration, so that particular paper made it onto the cover of PRL in June 2000, 5 minutes, in June 2000 of last year. Okay, so now, okay, so very briefly about the non-stationary states, right? So non-stationary solutions. So essentially, why they can also be universal, they can have non-universal self-similar asymptotics, right? So they have also scaling regimes. And very interesting ones, for example, so if we do a self-similar substitution like what is shown here, right? So there could be two kind of self-similar solutions. One where all the self-similarity parameters can be determined from conservation laws. So in Zeldovich, Barenblatt terminology, it's called first kind self-similarity. So the second one is where you can't do that. It's not possible to do that, and you have blowup in finite time, and you have to solve a nonlinear eigenvalue problem. You can't use conservation law because the part which it becomes self-similar contains only tiny amount of the initial conserved quantity. You can, the classical example, you can compare point explosion in air, in atmosphere, and it expands as the famous Taylor solution for shock wave. You can derive speed of propagation of that. That's first type self-similarity. Or you can have, you can take a sphere and remove air from it, right, vacuum, and it will collapse. And that self-similarity you can't derive just from conservation of energy, because most of energy will be at infinity. So that is the second kind self-similarity. And so, and here, in fact, we do have both kind of self-similarity, one for forward cascade, first kind self-similarity, and another for inverse cascade, that is second kind of self-similarity, and that is precisely associated with this blow-up behavior, non-equilibrium, Bose-Einstein condensation. Okay, so maybe I just going to wrap up, and want to show you details. So there were some also sort of numerical simulations testing these predictions for self-similar solutions, which seem to work quite well. But what I'm going to just finish with is that this blow up one. Okay. Okay, so essentially that is perhaps one interesting thing. So the criterion for blow up, right? So here's something that we can formulate as a hypothesis quite rigorously, even though there is no mathematical proof yet, right? So that that's to relate this condition, as I told you, where you can't find a related spectrum, and therefore there has to be condensation, right, at zero frequency, and the blow-up behavior. So basically, it's saying that every time if you have satisfied condition like this, you won't be able to find relay gene spectrum, right? Not only you have the final state, you have macroscopic fraction of particles at zero momentum, but also it will happen in a blow-up way, right? And so this is so some particular example of one blow-up solution was given by mathematicians in Bilbao by Miguel Escobedo and Juan Velázquez. But what we're saying, it is quite a general phenomenon, and any time we are below this boundary, we're going to have this blow-up. Right. Okay. So okay, one thing I did not talk about, but it's perhaps a little bit of more detail. So for realizability of scaling solutions, we not only we need to check the convergence of integrals, right? But we also need to check stability. Like with any solutions that we have in mathematics, if you have a solution but it's unstable, it's irrelevant, right? So here the theory exists for steady-state solutions, Kolmogorov-Zakharov type, but completely absent for the self-similar scaling regimes of evolving turbulence, in particular for blow-up ones. Okay, thank you.